curves. So first, let's look at the graph here. So you can see there are one straight line and one quadratic graph. So let's see the quadratic graph first. The quadratic graph is y equals x squared. So let's say that's our quadratic graph, y equals x squared. And then we give it a function of x, right? And then there's a straight line, which is mx plus c, okay? For that straight line, we don't know the exact parameter m and c, but we can have some information like the c must be greater than 0. That means the y-intercept must be positive and the gradient is between 0 and 1.3, which we use m as a symbol. All right, so that's our straight line, y equals mx plus c, which is gx. Okay, so let's look at the question. So let's say the curve and the line intersect at x equals alpha and x equals beta. So that two x coordinates for two intersecting points between the line and the curve. And that's one piece of very important information. Suppose that the combined area of area 1 and area 3 equals area 2. So that's such a important information here. So the combined area of area 1 and area 3 equals area 2. What does it mean when you look back to the curve? That actually means the area of 1, okay, the area of 1, which is between the curve and above the line, plus the area of 3, which equals the area of 2. Okay, so area 1 and area 3 are those bounded areas which are above the straight line and under the quadratic graph. Area 2 just the other way around. So, and okay, so that's the information of the about of the area. So then what you're going to do, you need to determine relationship between m and c. So m and c, they are just the parameter for the equation of straight line. That means the gradient and also the y-intercept. Considering the relevant definite integrals, so you are full working including the necessary property definite integration. So that means you need to use definite integration and the information that the combined area of A1 and A3 equals A2, and in order to establish a relationship between M and C. Okay, so pretty much what we can use, what we should start with is that information. Okay, so let me copy and paste the information here over here to give me more space to work on. So let's think about how can we represent area 1 using the integration. So we see area 1 is under the quadratic and above the straight line, and quadratic means y equals fx and straight line means y equals gx. All right. So our first integral about area 1 should be a definite integral of the difference between the one above and the one below, which is fx minus gx. It must be fx minus gx because fx is above the gx dx. Okay, and don't forget your lower limit and upper limit. Where's the lower limit? For area 1 is from the line x equals minus 2 to alpha. Okay, although we don't know what value of alpha is, but you can still write the limits. All right. Right. Then let's think about area 3 and area 3. Okay. So when you look at the green area, it's still below that quadratic y equals x squared and above the straight line, the linear one, y equals mx plus c. So that means you will have some integral, again, using fx minus gx dx. So what will be the limit you will have in that case? The limit should be between beta and 4. Okay. All right. And last, which is lastly, we're looking at the A2. Okay. So it's a bit different between A2 and the other two areas. For A2, it's the other way around because you will see gx is above the quadratic fx. All right. So basically, what I need to write is gx minus fx dx. All right. And by doing so, you need to consider the lower limits and the upper limits as well. For that purple area should be from alpha to beta, as you can see. All right. Right. Okay, that's what we've got from definite integration. That 3 definite integrals. So my question is, the next question is, okay, can I combine them to simplify the integration so that I have a chance to get some information between m and c? Okay, how can we reduce the number of definite integrals? That's what I'm now looking for. Okay, so let's see. The good things about these 3 integrals are they are all about fx and gx, but of course the last one gx minus fx. And okay, and also they are lower limit, upper limits. They are not the same, but they are connected. So you see, from -2 to alpha, and then that's alpha to beta and beta to 4. Okay, so how can we use those information to combine those integrals into one, which can be easily simplified? All right. So, and I noticed one thing. If that's gx minus fx, which would be different to fx minus gx, how can I reverse that? Okay. So that's what I'm going to do next. So first, I'm going to keep my left hand side intact. And what I'm going to do is just focus on my right hand side at the moment. All right. On my right hand side, I would like to make my integration into fx minus gx. Okay, so you see, oh, sorry. The difference between the line above and the line below is just I reversed. After reverse, oh, what happens? My fx and gx. I swapped them, but the consequence of doing that is like you need to have something minus outside, right? Because you reverse the subtraction of the two numbers, just like, okay, can you just give you one quick example? For example, if you have 6 minus 3, how can you make 6 minus 3 equals 3 minus 6? So 6 minus 3 is 3, 3 minus 6 is minus 3, right? So the only thing you can do is you put a minus sign in front of the right hand side, then the two sides will be equal. That's what I'm doing here. So if you swap that subtraction, then you need to have a minus sign outside. All right, but the good thing is right now we unified all the contents we call integrands. That means the content of integration into fx minus gx. And the next thing I'm going to do is I'm going to move my right hand side into the left hand side to see what happened. All right, so let's see. That's my left hand side, right? So what I'm going to do is move that right hand side to the left hand side. And to do so, because that's minus, if I move the whole thing to the left hand side, it needs to become plus. Okay, it becomes plus. Okay. Okay, and what happened to the right hand side? Because you bring the whole integral to the left hand side, so that means the right hand side becomes 0. So right now, okay, let's have a look. What happens here is you have minus 2 to alpha, and then, okay, that alpha should connect to that alpha in the last integral from alpha to beta, beta to 4. Okay, so can I swap the green and the purple integral again? So that's another one I would like to do. So first one, I'm going to copy and paste my first integral here. Then I'm going to move my purple integral into the second place and my green integral to the last place. So I'm just playing around with the integrals. So of course I can do it, but what's the advantage of playing that trick? So right now you can see from minus 2 to alpha, that alpha is the same as this one, and also there's a beta here. I would say, let me use this color. There's beta here, and that beta is the same about that one. Okay, so here there's another very nice integration property you can use. If all these, the upper limit of the first one equals the lower limit of the second one, and so they can be combined together to form one. Okay, so the idea here is one of the properties of definite integral. Okay, let me write here. So that's a property. That's a property, sorry, of definite integrals. Okay, let's say if I have a plus b, a to b, so some kind of function, let's say hx dx, plus another integral from b to c, hx dx. All right. So can you simplify that? Yes. All right, because that lower limit and the upper limit of first equals the lower limit of second, then you can always combine them into AC from A to C hx dx. All right. So it's not very difficult to prove it. If you don't know how to prove it, you can see me in person. I can show you that, but it's actually intuitively true when you consider the boundary area from A to B plus the boundary area from B to C of HS, then it must be equal the boundary area from A to C, right? So I'm going to use that one to combine my three integrals here. So first I'm going to combine these two from minus 2 to alpha, alpha to beta, and you have to make sure the content of the integral must be the same. That means fx minus gx here. All right, and so if I combine them, what I'm going to get is from minus 2, alpha the same, so I'm not going to write alpha again. It becomes like that one. All right, so and at the same time, I'm going to move, because I haven't touched the third green integral, so I've moved down one more line. Okay, over here, you can see minus 2 to beta, beta to 4. That means what? That means you can further simplify it to combine them into 1, becomes minus 2 to 4, which is fx. Let me circle them, okay? So the beta, they are the same. So that's why you can combine them to this one. Okay, so let's see the whole picture, what we've done. So we start with A1 plus A3 equals A2, but then I play tricks on those integrals. I try to uniform their contents, And then in the end, at first there are three integrals. Okay, and then in the end I combine them into just one. It becomes minus 2 to 4 fx minus gx equals 0. Okay, and so what's the advantage of doing that? Because we know what's our fx just x squared, what's our gx, which is mx plus c, right? Okay, so right now you could see it's an integration of two function in terms for x and some parameter and equals 0, and you can definitely simplify that. Oh, sorry. So let me expand it a little bit. Then we will know what should we do on that one. So first of all, you try to split your integration into 3. I'm going to take that m out, and I'm going to put that c out as well. So it becomes 1 here. That's 0. Okay, so the first integration we understand should be x cubed over 3 minus 2, 4. The second one should be m, x squared over 2 minus 2, 4 minus c. Okay, and that one will be x over 1 minus 2, 4 over 0 equals 0. Okay, what will be your first one? Okay, first one you put that 1, 3 out, and you have 4 to the power 3 minus 2 to the power 3 minus, okay, m over 2, and that will be 4 square minus 2 square plus c. Okay, you have 4 minus 2, and e equals 0. All right, then you will have, like, that would be 64 plus 8 minus m over 2, 16 minus 4 minus c, which becomes 6. All right, so remember minus 2 cubed should be negative 8, and minus become plus. The second one, minus 2 bracket square is 4, okay? And all right, so what will you get from this one? So the first one is actually 72 over 3, which looks to me 24. Okay, and the second one is 12, so that will be 6m, and that's 6c. So remember what the question is about. The question is to find relationship between m and c. So we are nearly there. Okay, we're very close. All right, and what I want to do is to put like m as subject. Like if I put my minus 6m to the right hand side, so I got that one. So you see the number 24, 6, and 6, they all divisible by 6. So let's try to divisible. Let's try to divide both sides by 6, and that will give you 4 minus c equals m. What you like, you can rewrite that as m. So that's the relationship between m and c. Okay, so how remarkable it is from just the information that you need to get the two area equals the 1 under the straight line, and you can go all the way from 3 integrals becomes 1, and then you simplify all the expressions, and you will get m in terms of c. Okay, so that's pretty much what we need to do for the part A of that problem solving question. Then next we are going to further that question by looking for the value of alpha and beta given difference m. That means you will get different C as well. Okay, but that will be in the second video. All right, thanks for watching. Okay, see you in next video. Thanks.